Ryan, I think you can hear me, right?
Correct, and we're now recording.
Awesome. Welcome to day 2 of HOTI Interconnect 29th edition. I'm Manjunath Gorantla, and I'm the general chair for the conference, and with me is Taylor Gross, who is vice chair. So we'll kick off the day with Dan giving a keynote. Dan is the executive director of Texas Advanced Computing Center. Following that, we have a very busy schedule. We have 4 sessions. We have after the keynote, we'll have a congestion control session followed by next generation network interfaces session. And after that, we have a sponsor talk, and following that, we have a data center networking session. So we have a very packed schedule, and the main conference it will end today, but we have a very busy day tomorrow too. It's tutorials, and again, it's very packed schedule for tomorrow. And we had a lot of interest last year, so some of the tutorials is updated and are included again. So we have 2 tracks tomorrow, and the it's running parallelly. So it's going to be interesting, and also there's new tutorials, particularly in the track 2. So you might want to attend both of them. So in case you didn't join yesterday and you are joining today, just a bit of housekeeping, and you are already here, so you know how to log into Zoom. But in case you want to navigate back, there is a link from hoti.org/program where you can join. You already know this, but in case you are joining today, we have all our recordings. Typically, a few hours after the session ends, we have a recording uploaded. But by end of the day, we have it. And probably in a week or 2, we will have it uploaded to YouTube. So on the right corner, in case you are on a web interface and you want to switch to your app, you can switch there. And the interactions, questions to the sessions, speakers, presenters, session chairs happens through Slack. Please join Slack, both speakers, attendees. And if you want to watch a recording from yesterday, you can go to sessions, and there's multiple ways to get it. This is another way. Okay, and the most exciting thing yesterday at the end of the day was we had a trivia, and we have 3 winners, and congratulations to all of them. Slack, you should have a link to join the Slack. It's either your registered email will have it, or we have posted in multiple channels on the chat channels, Zoom chat and everything. So if not, ping one of us, we will provide you, we'll direct you. So once you join HOTI Interconnect Slack, you will be added to all channels by default. You can ask questions in a specific channel for a specific speaker. So please use Slack. And I would like to thank again the organizing committee. It's all volunteer committee. We work 7 to 8 months. We meet every week to figure out the logistics, content, everything. So I would really like to thank all the organizing committee members. And of course, we get a lot of help from our steering committee as well. And you've seen that they are very active as well. So with that, I would like to thank sponsors. Without them, this event would not be free. And without them, we would not be able to conduct. I would like to thank GigaIO, Nutanix, and Intel for Diamond sponsorship. And also we have talked from them today. Please join. I would like to thank Meta for Platinum sponsorship, Arista for Gold sponsorship, Lenovo and Algologic for Silver sponsorship. And of course, we get a lot of support from IEEE as well. So thank you all for attending. Have a great conference rest of the day. So that's it from me. Ryan, it's all yours now.
Okay, thanks, Manju. My name is Ryan Grant. I'm from Queen's University in Canada. I'm one of the PC chairs for this event, and it is my distinct pleasure to introduce Dan Stanzione. He's the Associate VP for Research at UT Austin and Executive Director for the Texas Advanced Computing Center. Dan's been the PI for several big systems, the most recent of which is Frontera at TACC, which I believe still holds the record for world's fastest supercomputer on a university campus. So I look forward to his talk today. I hope you do as well. He's going to talk to us about Interconnects, Accelerators, and Disaggregation experiences at TACC. So Dan, please take it away.
All right, thanks very much, Ryan and Manju. How's the audio? Still good?
You're good.
All right, we'll just get the slides going here. The normal Zoom start, which we all know and hate. And there we go. So again, thanks very much for the invitation to be here and the introduction. Watching everybody join on the Zoom session, and I see a number of old friends and a lot of names I don't know. So the old friends can tell me why I'm wrong in the long period, and the rest of you can just tell me why I'm wrong today. But in terms of what we're about to present here, this is a talk about disaggregation, which I know has been a, no pun intended, hot topic here. It was the subject of the panel at the end of the day yesterday. But really, it's less about the technology of disaggregation and more about how we operate as a center and how we make the decisions to, whether or not we include these technologies in what we offer up to our users. And sort of in various ways, we've been looking at this for a number of years now, and let you know sort of where we are in our evaluation. So for those of you who don't know me or may not know anything about TACC, let me just do 3 or 5 minutes on who we are and what we do, because I think our operating context is pretty important for the way we think about disaggregation. So we operate a lot of relatively large supercomputers, Frontera among them, which is 3 years old now, but still a top 20 machine. But we operate them all for the National Science Foundation, whose logo is prominently featured there because they give us all the money. So therefore, you put their logo on stuff pretty constantly. The Stampede 2 system, which is a little older, there on the left side of the slide, are our 2 big platforms now, with about a dozen smaller platforms that we run. And the follow-on to Frontera will be a machine as part of the Leadership Class Computing Facility, currently codenamed Horizon. Note to DOE, stop stealing my names. But so it's Horizon. I'm claiming that now for 2025. But and so that will be a much larger follow-on to Frontera that's coming soon, and where we're really thinking about how we integrate some of these technologies into what we do. So and again, we're really a user facility at a very large scale for the National Science Foundation. People are always surprised that about 8% of our cycles goes to Texas, and 92% go to other users around the country and around the world and their partners. So through our federal and open science funding, and we support literally thousands of projects. Lone Star 6 there is one of our fully immersion cooled, which adds some challenges for disaggregation. One of the newer systems, Frontera, is direct liquid cooled. We still experience both of those, but we put out 7 billion-ish core hours a year. Right now in the data center, we have 20,000-ish servers. So we do run at relatively large scale, really large scale for a university, but even for, by cloud standards, we have sort of similar scale problems when we get to the tens of thousands of servers. But we run all of our machines strictly for unclassified open science. So this was sort of my 2021 highlight slide where, multiple of our users had the covers of Science. We had a computing and science and engineering special issue, everything from that water transport as a materials work. It's membrane for a desalination project. The other one is a turbulence project. And I'm still working on 2022. But generally, if there's a big thing in science that you see in the New York Times, we're in there somewhere. From, in May, when they had the unveiling of the first images of the black hole from the Event Horizon telescope, we put millions of hours into some of that image processing for that. In July, when the James Webb Telescope came up, that's actually some of the PIs for one of the instruments, or one of the surveys on the James Webb in our Viz Lab, looking at display walls of the first images that just found one of the earliest galaxies ever detected from the faint light in those images, and that's sort of the UT contribution on that project. This one I found by happenstance, but if you read the New York Times this past weekend where they talked about the possibility of megastorms in California, I had to dig back through the science papers and the references, but eventually all that data is published on one of our systems too. So through our Design Safe project. So if it's a big science story somewhere, we're involved. And so just a few more highlights. So I don't want to spend all my time on this, but things that are coming down the pipe that will have big stories in the future, that is out in nature. We work with the IceCube project, which is this giant neutrino observatory where they basically instrumented a cubic kilometer block of ice. Important to do that while we still have cubic kilometer blocks of ice, but it may be melting cube pretty soon. But to do neutrino detection, we do biomedical work with nanoworms, little magnetic wiggly structures that you can get through blood cells for delivery of medications to tumors and to keep that toxic stuff out the rest of your system. And we simulate whole galaxies and stuff like that. So this is a machine learning hybrid workflow, which actually really impacts the disaggregation story, where we're using low-res images in some parts of the universe after training a machine learning model to upscale those images by Tiziana over at Carnegie Mellon. So that's just the kind of things we do with computers in a nutshell. The gist being we're mostly focused on the sort of larger jobs, bigger simulations, and we really push interconnect performance because with big simulations, we're coordinating a lot of mostly MPI communication across those. And so that has a lot to do with the stuff we build. So our view of the sort of systems world today when we build stuff. So again, first thing to remember is we're a user facility. So whenever a vendor comes in and says, well, you just modify your code too, we're like, stop right there. Our best estimate is Stampede 2 has seen 4,000 different binaries over its life, right? And we didn't build any of those. So, we have very little control over what our users do. And we have a lot of users. I mean, we can kick off the really worst ones, right? If you're doing 64-byte IOs in Java, your time on our systems is very limited. But but we have thousands of applications. And as I put on the slide, and a lesson I learned from Don Becker, who I see is in the attendee list here, and is the only reason we get to deal with networks from Linux, is thanks to Don. But most of them are like all software in that they are poorly written crap. So things I learned from you, Don. So, but to be a general purpose and shared open environment, we have, like on Stampede 2, that's one of the systems I showed in the beginning. There's 16,000 users that have SSH access, about 2,000 use it in a given month and actually log in, and about another 50,000 come in through some version of web services. So we really have, this is not a tightly controlled enterprise environment. It's a wild west of computing where people can do whatever they want. And in terms of interconnects, not even going to get into the processor side, but on the interconnect side, right, we have an Ethernet network. That's just so it can be friendly and you can SSH in and see a terminal, right? It's establishing the IP-based connections to the machine. It's where the monitoring and the out-of-band stuff goes, but it's really a truly crappy network. It's, we don't spend any money on it. It's deeply oversubscribed because we understand the use cases for it. So when people say, well, you could run over your Ethernet network, the answer is almost always no, because then we put in a real network, which is what this conference is about. And typically for us today, it's InfiniBand or OmniPath. We just retired the old Cray network, but Slingshot would be a candidate here. We have a big test bed with Rockport networks. They're all optical one at the moment. And that interconnect is where the real work happens. So, and again, to distinguish us from some enterprise environments, we don't really do a lot of oversubscription, even rack to rack, right? So in fact, the top picture is one of our InfiniBand core switches on Frontera. The bottom one is an OmniPath core switch on Stampede. As you can see, we put a lot of care into wiring for serviceability, so we can get parts in and out of those switches with the wiring. In fact, the thing on the right shows you our sort of side channel where we're resorting. We have between those two machines and that are in the same room in the data center, they have about 150 miles of rack-to-rack fiber in them. Because we really want to have full bandwidth, bisection bandwidth across the machine. I'm sure Keith's talk later, he'll talk about some of that. So So the secondary network here, the InfiniBand or OmniPath network, carries all the file system traffic, so all reasonable IO and all the node-to-node messaging. And as a result, it's a fat tree without much oversubscription. We're pulling 36 fibers out of each cabinet to do that at 200 gigabits in the InfiniBand case at the moment. So 7.2 terabits of bandwidth out of each rack, across 100 plus compute racks. And although the bandwidth is important, and more important for the IO, what we really care about is the latency when it comes to message passing. And so we're, 900 nanoseconds in rack, and across the full system, 100 racks, 100 meters of fiber, worst case, we're sitting at less than 2 microseconds across the full system. So again, for our MPI version, latency is the dominant performance driver when we have to sync up these big jobs. And people say, well, what about the single node jobs and things like that? I actually just did an analysis for a site visit, and we've run 1.1 million jobs on Frontera this past year, and 4 million overall at this point. 550K of that 1.1 million were single node jobs. They ate less than 3% of the cycles, right? So 45% of our jobs, but 97% of the compute time we deliver is MPI code, right? So MPI really matters. Bandwidth and the IOPS matters more on the IO side. So naturally, given that they have totally different requirements, we run both those workloads over the same network. So, and this is just on the rack side. And so actually fairly important thing as we talk about disaggregation, space for cables is at a premium. So that's a Frontera rack, and you see that there's, the power is sort of the closest to you layer of cabling, and then there's the water manifolds running up and down. And so the inlet and return water to each node are the next layer of piping, but it works like cabling when you have to put it in there. And then the yellow there is the Ethernet, and the blue fibers are coming out of the top of rack switches. Hard to see. There's black copper for the InfiniBand in the racks, and we're at 84 nodes per rack. That's a 60,000 watt rack. So, you only want to interrupt airflow so much, but the cabling's gotten pretty dense. You get up to the shoulder, reaching into the server through all that cabling at this point. The one on your right there is an Immersion Rack that we have. That's actually a 70,000 watt rack around some AMD CPUs, 84 nodes that run way above their stated top power, but it's about 840 watts per node, typical operating power there. So, and again, the yellow is the Ethernet, the black on the right-hand side is the InfiniBand coming out, and the black on the left-hand side is the power jumping out. So in immersion, and again, space for cabling is at a premium. So as we think about adding more networks and using more PCI slots when we have this kind of density, and frankly, we maintain this kind of density to keep that latency down, right? Less cable length over, 100 racks of this stuff instead of 200 racks of this stuff, really improves our latency. And at this point, 15% of our IB latency is speed of light and fiber. So we'd see a pretty serious uptick if we did that. So if we, went less dense and made a bigger physical footprint for the machine. So, so to get to the actual topic of the talk is where we on sort of disaggregation. So, and here I didn't define disaggregation because I think if you're at this conference, you probably know what that is already, but we're running a number of different experiments in a number of different ways. We have a Giga IO experiment in-house. That's the one actually pictured there on Lone Star. That's the expansion chassis on the top and the cabling running down to the compute nodes. So we actually can physically make all this stuff work. That was one of our criteria on this. But so Lone Star 6, we've been testing Giga IO mostly with GPUs for reasons I'll talk about. In Chameleon, which is sort of our CS test bed where we let users override the software stack. We're running Liquid, and then in a system we're partnered with over at Texas A&M, we have an even bigger Liquid install. So that's where I pulled some benchmark data from. We're starting to look at Fungible. It's not in-house yet, but we're going to do that. Related, and so, Giga IO and Liquid are our classic sort of external PCI bus kind of disaggregation, soon to be CXL. But you can see other networks working in disaggregated hardware. Fungible is over Ethernet, for instance. So, we have about 400 nodes of Rockport installed that we've been testing, to try and do some at-scale testing of the topologies work and things like that. Again, Slingshot's always an option for us, and we've just put in a DPU test bed to look at, more processing in the network path to improve our particularly MPI performance. So on the interconnects. So those may play a role in future versions of disaggregation, but right now I really want to focus on the sort of PCI level disaggregation. And so although GigaIO and Liquid are fairly recent entrants, this actually isn't our first foray into bringing the PCI bus outside of the machine. So if we go back almost 10 years now, which is hard to believe because I feel like I wrote it yesterday, we built a machine called Wrangler that we proposed in 2013, which in disaggregation terms is a long time ago, and actually put into production in 2015, and has since been retired because that's 7 years ago. But we used the DSSD NAND flash arrays connected over an external PCI fabric to the compute boxes. Schematic on the next slide, but 96 servers had about a half a petabyte of shared flash, which seemed like a lot then, with a goal of getting a terabyte a second, which in 2013 was sort of ridiculous. Pretty doable over a flash-based file system now. But the notion of flash-based file system was hard. In 2013, most SSDs were over SATA and hard to put on the other end of the network. So we actually deployed this machine prior to the release of the NVMe standard and years prior to the release of the NVMe over Fabric standard. So this was sort of our first foray into how this sort of over Fabric storage disaggregation might work. And it truly gave us unprecedented IOPS capability, lots of different interfaces. 2013 was back when Hadoop might have mattered as a way to do things. So, and I will say that, lots of lessons from this machine, but in every technical way, it was a success, right? It did all the things we said it could do. In fact, you may remember the company DSSD, that they had their version of success, meaning that everybody we originally met with made a lot of money. But in the time that we worked with them on this project, they went from a company that had 6 employees who were all engineers to an organization with more than 500 lawyers. And somehow that was considered progress. I'm not sure how that works, but if you remember the stories, DSSD got acquired by EMC for a price that I actually know, but I'm not supposed to talk about, but had billions in it. And then was in turn acquired by Dell in a $50 billion deal, and then of course shut down. So all in about a 5-year span from start to finish. So, but nevertheless, we built the system, we ran it for years, it actually worked. And for really small writes, and we were comparing to hard drives at the time and SATA SSDs on the curve on the bottom, it was 400 times better than disk. So obviously that's a huge win, and we do that all the time now, right? As the company made billions and then got shut down. So, so what did we learn from all this? So, well, the first thing I learned is that the supply chains around little PCI switch chips and all 50-cent chips, as we have learned in the last couple of years, painfully once again, is that if you're making $1,000 silicon, fabs care and things mostly stay on time. Well, less than they used to. We've not had any problems during the pandemic getting big expensive processors, but getting the little firmware chips and the power supplies has been a pain in the neck. So same thing here. We relied on a 10 or 12 port PCI switch chip, making it to market in 2014. I think they finally shipped that in 2020. Probably really important chips for Liquid and GigaIO at this point. So we re-engineered it with 4-port switches, and we could only get, or 8 ports, but we could only get 4 DSSD devices to each server. Still lots of cables, because we had to have 4 PCIe breakout cables coming out of each server to do that. The original plan was 10. But again, it all worked as advertised, and we were able to present as users a parallel POSIX file system, HDFS, database services, mostly over Postgres, and then an object store API that they could use by 2015. And so the distribution of how people use that is probably what most of you would guess. Over the life of the machine, 90+% of users only use the POSIX file system interface. And if that worked for them, great. But if it didn't, they lost interest really quickly. So we did get one end user workflow. It has particularly nasty IO code that we still deal with on Frontera to this day for a big quantum chromodynamics problem, where the whole workflow got 12x faster because we could really throw a lot of IO at it. But that wasn't the norm for speed up, because of course, once you remove the IO bottleneck, you introduce all the other bottlenecks that the code has. But the database interface really gave us the best performance. Just a huge difference over database on disk. which mattered to all 3 users that really did large scale database in scientific workflows. It's just not a big use case for us. You mostly, if you have structured data, you probably put it in HDF5 for the big workflows, or NetCDF or something similar. So, but it was, lightning fast. And for a few projects, we saw huge improvements. The HDFS performance was better than HDFS anywhere else, but the rest of Hadoop still sucks so much that hardly matters. And 0 end user applications were ever built on the object API, which is not that unexpected. But so in the end, users saw benefits, but they only, for the most part, saw benefits if it was completely transparent to everything else they did, right? No user intervention required to use any of it. And again, for many of them, we fixed their IO bottlenecks, which just exposed all their other bottlenecks, which limited how much they did. Cabling was pretty much a mess, because again, we added 400 PCI thick cables, because we were doing sort of point to point without any intermediate switches. So 400 extra thick PCI cables in a 96 node system. And then of course, the biggest sort of quasi problem we had is that, but is something that catches a lot of companies, is the commodity technology, in this case, NVMe and NVMe over Fabric, caught up. And that's how we do all flash file systems in our systems now. It's all NVMe based. But it made that advantage less relevant as the years went on, right? So something that was way ahead of things in 2014, by 2018, you could get NVMe, or 2019 is when we deployed our next one. The software still needs work, but it's come a long way. So, and then also pretty importantly is, although we had a few instances of extreme speed up, it was pretty expensive for the average speed up, right? And the retail price of the boutique solution, not that we actually paid the retail price or anything close to it, but in terms of scaling it up, ultimately outweighed the performance advantage that you could get from it. So all important lessons as we look towards this new generation of disaggregation. So so back to our general eval process and how we make decisions about the stuff that we put in production. And there's this looks sort of random to the outside world, I know, and they feel like we reject everything, but we really do have a process for this. And the sort of steps that I make our staff go through before I'm willing to decide to buy or build any of this is, first of all, is there an actual reason we think it will make things better, right? What's the theory here? What are we trying to accelerate? What's a big slice of the workload, et cetera, et cetera. Then there's the does it actually work thing, right? There's the very common vendor claims, and then there's what it actually does. So we have to prove that it actually works, and then we have to prove that we can make it performant, right? And do work at that level that we think it should work at. Then to the transparency thing, can we make it usable for normal people on our systems and not some crazy thing that you have to go through special this and special that to get to, because the experience is most users will just ignore that given the opportunity. So, and we don't have enough leverage on them to force them to do it. So it needs to be usable for normal people. And then finally, if all that stuff works, is it actually worth buying, right? Is there an economic model that makes sense? And so I want to spend the rest of the talk sort of running through these 5 questions. So, with hopefully an occasional example. So, but not for this one. So could disaggregation in theory make things better? And the answer is yes, right? So one of the biggest challenges we have is picking system configs, given that we have all kinds of workloads of all different shapes and sizes, and it's pushing on a rope to ask our users to make software changes to deal with that. So typically what that means is we tend to put a massive amount of hardware in one sort of homogeneous partition. So using Frontera as an example, there's 8,400 identical compute nodes, all CPU compute. So that's the big piece. And then we have smaller amounts in various specialized subsystems. So for instance, on Frontera, 3 or 4 of them actually, but we have some NVDIMM based very large memory nodes for things that need large memory, but just 16 of those versus 8,400 for the CPU nodes. And we have 90 quad GPU nodes. So we felt like quad GPUs were sort of the sweet spot. But that does mean that, we do that for a reason, to keep utilization high in the most, sort of most common cases. But there are nonetheless plenty of load conditions where some subsystem has idle capacity while others are oversubscribed, right? So clearly just, the base of that, right? If you can't use the GPU nodes and they're sitting there idle while the CPU nodes are waiting and there's idle CPUs there, we're not optimal, right? So there is room to get better. So I do want to point one big caveat in this before we go on to the next question, which is a lot of this for the GPU side is based on the current deep learning workloads. And my view on those is, although they are also horrible and crappy code, they're not really any more horrible and crappy than the rest of the code we see, but they're in many ways still very immature and kind of all over the map. Some, and in many cases, they're limited by the shared GPU address space that you can run them on. So, so they'd say, well, I don't fit on 4 GPUs because of GPU memory anymore. So build me a box with 8 GPUs, or build me a box with 10 GPUs or 16. I think it's fairly likely that that's an artifact of the tools that they're using and not really a constraint on the algorithm. But it turns out we've actually solved this problem before. So, and I was like, so I want to talk about this when I was making the slides yesterday, and I decided, yes, I do. So we have a 2-slide detour because I think it's a relevant lesson, because it does seem like we solved the same problems over and over again. So, so thinking about how many GPUs do we put in a node, right? So, the how many GPUs per node debate is what I like to call the welcome to problems we solved in the 1990s, but use different words. So the AI guys have to reinvent it, debate. So, because we went through sort of this exact same conversation. Many of you remember it really in the 80s and 90s about whether we should build giant shared memory machines or lots of smaller machines in distributed memory clusters. And the gist of this argument, where there are a lot of great engineering designs in the shared memory camp from companies like Silicon Graphics and Data General and Convex and Sequent, Unisys, Honeywell, who can forget, $2 million for an 8-way Itanium server. And in the distributed memory camp, there are companies that aren't currently out of business and bankrupt, which pretty much settled that argument, right? So, is that if you built big shared memory machines, you really don't do it anymore. And if you survived, it was because of the part of your business where you didn't do that. And the reasons we didn't do it haven't changed, right? Hence we think of, should we build big shared address space GPU machines, or should we just do a bunch of distributed memory GPU machines? Programmers, application writers are always going to pick shared memory, right? Shared memory systems are inherently easier to write software for. It's easier to optimize and performance tune. So every application writer would like them, right? It's just an easier abstraction to use. At the same time, the lesson that we have learned over and over again is that if you want to build a giant shared address space, you have to build a bus, or you can simulate it, more on that in a minute. But and if you make a bus and then you have to do any kind of coherency across that bus to make sure one of the processing elements there hasn't updated the variable that another one is looking at, that gets exponentially more expensive as you scale up the number of processing elements, and works great at 2 and 4 and maybe 8, and then 16 and 32, it starts to get prohibitively expensive, and by 64, it all falls over. So, and you can sacrifice that, and you say, well, we're going to build a shared memory or distributed memory, but we're going to create a shared memory illusion over it with, locks and various programming models to do that. Then those same programmers will fall in all kinds of programming traps without ever knowing why, because none of those places where they're, going to this really non-uniform memory domain, NUMA style, it's implicit if it's shared memory, and it's explicit if it's distributed memory, so they could see where they were screwing up. So they just tend to work badly on the shared memory application. So inevitably, the hardware that's 10 times cheaper is going to win out over the 2 times more efficiency and ease for the programmers. And it did turn out, much to everyone's surprise, going back in parallel computing to the Seymour Cray, Danny Hillis argument about, if you'd like to plow a field, do you want to have 4 strong oxen or 1,000 random chickens? It turns out 1,000 chickens is counterintuitive, but it's what we want, because a lot of the algorithmic space ended up to where we can do a pretty good job with MPI and distributed memory type approaches. So I think it's pretty likely that Horvath is going to take over, or some other approach to doing good model parallelism in GPUs will come along. And we'll wonder why we ever built $100,000 plus GPU box, because that doesn't make any sense, and we should just do a couple of GPUs per node. So, so keep in mind, there are lots of analogs to this debate. We've had it in the past. The AI guys think it's new, but it's not really new. And those same engineering constraints are going to come into play at some point when they say, well, my natural language GPT-4 model can only run on 64 shared GPUs. And somebody will be like, yeah, but for half the money, I can run it at 80% the efficiency on 64 distributed GPUs. And then it'll just go from there. So that's my 2-slide debate on, whether or not we're going to have this problem of, do we need to put 16 GPUs in a box? And then do I have to buy 8 GPU and 4 GPU and 2 GPU boxes to do cost efficiency? That may go away. And so that's a business risk, I think, in some of this disaggregation stuff. So, that said, I do want to narrow the scope for the last little section here on these other questions, because there's a lot of things we can disaggregate, and each will have its own sort of separate value proposition. So we can do accelerators, really we mean any sort of PCI accelerator card at the moment. So whether it's FPGAs or IPUs or vector engines or, GraphCore AI accelerators or whatever it is, we can aggregate and disaggregate, compose. It's disaggregation if you're me, and it's composability if you're an optimist. So we can do that around accelerators. We can do it around storage, right? We can pull remote storage devices into locally appearing either block devices or file systems. And we can do it for memory, right? Either using like the coming CXL attached memories or, grabbing remote memory out of another node. All of those things are possible. And it is worth keeping in mind that we're doing all of this over PCI in the current generations, but things like CXL are coming, which does create distributed shared address spaces. And those kinds of future fabrics, next gen and V-Link, Infinity, whatever, in AMD, et cetera. So, but when we think about these, can't cover all of them today. So there's one that's more interesting to me than the other. So dynamically composing storage is great, and we're probably going to do more of it. But the question is, do I need like CXL or PCI level latency to do that? Because if I don't need that latency, then I can just use, say, NVMe over Fabric, right? And do it over a conventional fabric or, the InfiniBand or OmniPath Slingshot fabric we already have, right? So, and seems like it would be cheaper to have 2 fabrics instead of 3 to get to your storage. So, and yeah, we need better software layers to sort of dynamically converge that stuff, but it sort of feels like the entire storage industry is working on this, right? Whether you're talking about VAST or Weka or DDN Red, or, I could name 5 other ones that are coming, right? Everybody's doing this, master view of there's big pools of storage, and we can, in a dynamic way, we can put it together and present any interface you want, build file systems. And half of them will fail, but eventually some of that's going to work right. But so the software problem will get solved there. But again, looking back at what we've seen, bandwidth and IOPS are really our driver, not latency for IO. So we may not, I don't think it's a huge driver to do a PCI fabric right now to compose storage, right? I mean, maybe doing something over a relatively low latency fabric, using DPUs instead of main processors. There's a lot of things we can do there, but for PCI disaggregation, I don't feel like that's the driver. In remote memory, the opposite's true, right? We're in a space where we can see huge performance differences when things stop fitting in L2 cache and fall back to L3 cache, and the differences in nanoseconds, right? So, so when you have a NUMA, non-uniform memory access system, latency is going to matter a lot, right? And CXL may bring this down some, but I'm personally somewhat skeptical that we're going to see great performance on the remote memory stuff. However, we do build sort of ridiculous NVDIMM-based large memory servers now, because there are occasional cases, sort of corner cases, pre-processing, post-processing, where you just need the answer, and you don't care if it takes forever to run, and you don't want to buy a ridiculously expensive box to do that. So I think there's a niche use in the remote memory, but that's not something we're going to put, it's something we're going to put on a couple of percentage points of our nodes, not, 8,000 nodes disaggregation, because we can enable remote memory. So that leaves accelerators, which I think if there's going to be a killer app for this, this is probably it, right? Is dealing with accelerators. So I really want to focus on that as something to evaluate, but right. But as I've already noted, right, for better or worse, and it might change, but the current state of deep learning software is fit in the address space of the GPUs on one node. And putting anything anything over 2 GPUs really has some premium, but especially over 4 GPUs, there's a premium price on that in terms of buying the box because of the whole shared memory thing and lack of huge market. So I really want to take my last 10 minutes here and focus just on the GPU use case, right? So, and that's where we've been putting a lot of our effort. So back to my question list, does it actually work? Yes. So no real pictures on this, but with both of our PCI fabric evals, and actually the Rockport stuff works decently now, we can verify that things function like they're supposed to. And all I can do is report the facts here. As a public employee, I can't neither endorse nor not endorse any particular private vendors, but across Giga.io, Liquid, Rockport, yes, it all works. I can do that. And we can even do composability without rebooting stuff, which is such a wonderful thing. And we can make these, accelerators appear as pretty large nodes. So does it perform? And this is sort of a key question, and here we need a graph. So, and yes, it's not a DGX box, right? It is not, obviously, for all use cases, it's not going to be quite as good as, directly NV linked here. And here I'm using NVIDIA to mean GPU, because the others are not far along enough for us to do these sort of evaluations on. But but for NVIDIA GPUs, this is looking pretty much across A100s for the most part. The bottom chart has a few other things, but ResNet built on TensorFlow, ResNet built on Torch. We looked at some various DGXs tuned in different ways, and then faster here is the Grace is a conventional cluster with A100 nodes, and then faster is the, in this case, I pulled some Liquid data. We have shared file system working a little better there, but but we're getting sort of 80% of DGX performance on the big case. Plus, we can keep scaling past the 8, right? So it starts to catch up when you go to 10 GPUs there. So, I mean, again, in some use cases, it's just as good. It's equivalent. In some use cases, it's a little worse. None of them is a lot worse that we've seen. But yeah, this performs pretty well, and it's a lot cheaper than buying a DGX, so that's a good thing. So then it's like, all right, it works, it performs. Can we make it usable? And so the scheduling here is still a bit of work. I'll explain why in a moment, but we can do the Slurm integration, we can do the orchestration, so it's transparent, users don't have to do anything. So all that's cool, we can make it work, right? Physicals, installs, we've messed around with it. We can make the cabling fit, and there's ways to do that. It's not as bad as what we did for Wrangler. So, so it looks like physically there's no reason we can't do this stuff. So that's good too. We haven't really done a lot of Kubernetes work yet, because we figure that's where the vendors are putting most of their time. But we've done it with Slurm, we've done it with OpenStack. If those work, there's no reason to believe Kubernetes isn't going to work too. So, so we can make it usable. So then we get to the hard question. And the last question, which is, can we make the economics work on this, right? So it works, it's worth something. We know that. How much, right? How much of our investment in hardware would we want to divert into disaggregation? And this, as center director, is sadly the question I have to spend time on. So in other words, can it be sold profitably at good enough value for enough use cases that this industry is going to be worth it? Because there's been a lot of technologies that are pretty cool and that have corner cases where they work super well, and they still don't succeed in the market, right? So it sinks a lot of companies if you don't really understand this. And so there's still some work to do here, but I can tell you where we are on it so far. So, so basic facts, true facts, the kinds I like. There's a lot of alternative kinds now, it seems, but GPUs are expensive, right? Step one, undeniably cheap, unless you're Jensen, in which case, every time they get faster, they're even more of a bargain. So, but CPUs and GPU nodes can be underutilized resources, undoubtedly true. And different codes need different size nodes, and none of those codes are particularly malleable, and that is also true. So there are some other true facts that might dissuade from those three things, which are all sort of big pluses for disaggregation. GPUs are expensive, but you got to buy them either way, right? Whether you're putting them out in disaggregation or putting them in nodes, in the end, you're going to buy as many GPUs just about. So certainly having high counts per node costs non-linearly more, hence the SMP debate. So, but that money is going to get spent. CPUs and GPU nodes are underutilized, but really they're a tiny fraction of an overall node performance, right? If you have a standard x86 node and put 4 A100s in it, 7-8% of your performance is from those CPUs. Leaving them idle may not be the worst thing in the world. There is the fact that the software and the workloads can change. It's very slow. It's over a long period of time. It takes a lot of pressure to make it happen, but it could change. And, in this case, back to the how many fabrics am I crossing, we're adding a third fabric into our system now, which is going to make inevitably performance debugging tougher, right? Because there's one more thing that can go wrong. Not only do we have to physically deal with that, and we have a cost of the third one, but now you have to say, all right, my SSH connection went over Ethernet, and then I went over InfiniBand to the file system, and then talked over the PCI Express switches to the accelerators. Which of those things was the bottleneck again? And it's, ask your debugger to tell you that, or your profiler. Good luck. So, and there's the fact that, you have to factor in that we don't really pay anywhere close to the real price of these things. When we buy them at scale, HPC has always stood for half price computing, and that's really only if you're bad at it. So, so we need to fit all those things in. So this takes some analysis. I'm going to show you a little analysis. It takes a lot of analysis, but as I sat down to do some of this, turns out my queuing theory and my use of random variables, the one or two of you who went to grad school with me on the call know this, and even my programming are all a tad rusty at this. So when I sat down to write the Python to simulate this, good luck. So I have some hand-sized examples to show, but given that, can we make a case for some upper and lower bounds on the value of this? Sure we can. We absolutely can. And as predicted, by the time I get to the slide, I'm probably out of time. I actually do have like 8-10 minutes left, but let's just look at one sample scenario. So here I have two clusters where I bought essentially the same hardware, but a fully composable one with 22 nodes and 12 GPUs, and a more conventional mix that you see on a lot of campuses with 22 nodes and 12 GPUs. But in this case, 16 of the nodes just have CPUs, and then we have 4 nodes with 1 GPU and 2 nodes with 4 GPUs, right? And so you see lots of little clusters that look like this. And then we need to pick some workloads, but I'm going to show you, well, if you do an all CPU jobs where we choose to either reserve the GPU nodes for GPU jobs or not, and then a mix of CPU and quad GPU jobs, and I just made all the jobs run for an hour to make the graphics easier to draw. But yes, we do add a third dimension to scheduling when you're disaggregated, but we can run some metrics on this and compare things like turnaround time, utilization, et cetera, and get some feels for this, right? So if you have an all CPU workload, and to not do the complicated version of this, if you can use all 22 nodes in the static config, because you see you don't, if you use the 16 CPU nodes only in the static config, but you can use all 22 in the composable config because you're not reserving those for GPU jobs, you get 22/16 of the work done in any given time, right? So that's a 37% improvement in utilization and in completion time. If you choose to just schedule CPU jobs on the GPU jobs, you wouldn't see any improvement, but you're not going to do that because if you bought an expensive quad GPU node, you're going to save that for expensive jobs. And if you bought one, you probably have mixed workloads. So that's sort of a simple example where we see some advantage. The more complicated example is something like this. And yes, you have nodes in time to look at schedules in a normal workload, and then you have nodes time in that third axis for your disaggregated thing, in this case, GPUs, when you're doing it on a disaggregated cluster. But let's say I have a mix of size of CPU jobs shown in blue, and then I just have quad GPU jobs to keep it easy. I just did 2 classes shown in green here. And remember, I only have, well, in this case, I did, I guess, 1 quad GPU node. So, but they're an hour long, right? So that's how it would look on the static cluster. I'd end up with all those 1 GPU nodes unused because none of the jobs fit on them. I could make an extra 4 GPU node. So with in the disaggregated case, with those 4 GPUs that would have been in 1 GPU nodes otherwise, that moves job 7 around, which knocks an hour off my time to complete this. And so I see like an 18% improvement in utilization, 28% improvement in turnaround time across all the jobs here, and a 33% improvement in the time to complete the whole workload. Those numbers all sound good. and it would be great if that was the standard case, but keep in mind, there's a lot of conditions you have to make. So if you make the assumption that job 8 here, the big CPU job, arrived before job 7, and your scheduler was just trying to fulfill jobs as soon as they showed up, job 8 would have scheduled on those extra CPU nodes. There wouldn't have been enough CPUs nodes to compose for that, to put those GPUs on for that last job. And all those advantages immediately, well, turnaround time still has an improvement because job 8 runs sooner, but utilization, workload completion don't get any better, right? So there's figuring out how many of these mixes and what your mix is and how much it happens is important. So, but there are cases where, 18% utilization improvement is not ridiculous, right? But it's not going to happen every single time. So, so if we think of that in terms of cost, right, which is, again, how much of this do I want to put in my next big machine, right? So, but if that 18% utilization were average, right, and again, it's easy to contrive cases where it's better and cases where it's worse. Hence, you need a big simulation with a lot of random variables to really figure this out. But on the assumption that CPU nodes have a fixed cost, GPU nodes have a fixed cost, but you have a premium cost for a node that holds 4 GPUs and that everything gets discounted by the rate that I expect things to get discounted, right? I could justify putting about 14% of the system costs into disaggregation, right, of my total amount I'm spending on hardware. By the way, if you do this, where I just didn't want to draw a bigger picture, but if you double the size of everything and you use DGX nodes that are 8 ways, which have like a $50,000 premium in cost versus the price of the GPUs, then double the workload size to fit it all, then it works out to maybe 18% of your investment would make sense here. So, so summarizing it, seems fair to say, but you've won more experiments, but unless you can fill, unless in your normal workload you can fill every type of node all the time, you're going to see some utilization improvement. That seems almost inevitable, right? Sometimes small, sometimes large, but if you have a largely heterogeneous system otherwise, maybe you'll see about 15%, right? Again, there's confounding factors, right? If you need to run 10 GPU jobs and you don't have a 10 GPU piece of hardware, what's that worth to you, right? To add that capability, right? That's one that you just can't do otherwise. So it's not a fixed dollar amount versus buying a big 10 GPU box of some kind, right? So, if you only do that occasionally, you could buy cloud time to do that hypothetically. So what's it really worth to you, right? And the cloud time would be expensive, but not too bad. The time to get your otherwise local workload ported over to the cloud would be, roughly the rest of your life. But anyway, and this assumes that the disaggregation cost is purely additive to the system, right? It's all additional investment. What if we could replace one of the fabrics, right? For instance, pull out my InfiniBand fabric and send all my message passing over to CXL or PCI disaggregated fabric, right? And then reduce the amount of InfiniBand I buy. It's tough for us because we don't have a lot of oversubscription, right? And so every time I put in one of these other HCAs, I'm gonna have to put another InfiniBand HCA somewhere to get it out of the rack. But if you did do oversubscription at the rack level, we're already spending about 15% of our system cost on the InfiniBand OPA thing, between cards, ports, cables, et cetera. If you could replace some of that investment, then you can make a bigger investment in this stuff. So there are many caveats, confounding factors, but certainly there's value. So what can I tell you in the end is that, one, for us, disaggregation definitely opens up some exciting possibilities, but it's added complexity and cost. It definitely works. I expect it to work better once CXL arrives. But it's already pretty performant and it definitely adds value. The real question is how much of your system budget should go towards it, to which I don't have a definitive answer, but I can tell you my personal leaning is it's worth it to put it in some fraction of your system. It's tough to justify the cost to put it in every node. So the questions become, what's your job mix? What are those new capabilities worth to you? And what's going to happen if, maybe when, the deep learning software changes? But for us, the occasional remote memory node, the occasional big GPU job, be worth doing, some fraction of nodes for. So, but again, there's still lots to think about here. So, my hand fit scheduling assumes that your scheduling algorithm makes good decisions, right? And in this 3D space, do our scheduling algorithms really make good decisions. That yield performance is good as much better than our current two-dimensional utilization. So, and again, what's the real broad mix of workloads and what's the value prop for those other use cases that we ignored in this analysis? So, but there's a lot of good things out there, but a lot of research left to do. So I'm close to out of time. Wanted to save a little bit for questions, and I'll hang around for Slack questions. But let me say thanks to all the people at TACC that actually make this happen. Yes, that's a pre-pandemic picture, because I haven't had everybody in the building at the same time in almost 3 years. But thanks very much. I'm Dan at TACC if you need to find me, and I'm on the Hot Interconnect Slack. So I'll stop there. Back to you, Ryan.
Perfect. Thanks, Dan. That was great. Since we've got a little bit of time, why don't we start taking a couple of questions from Slack now? And if we don't get through all of them, we can continue the conversation afterwards. Sissy was asking how serverless architectures might impact these things. And I know that's been popular in cloud lately with all of the, this idea of doing small amounts of data where you don't have to worry about what are servers again. Do you have any thoughts on whether serverless makes sense from an HPC computing perspective and how it might impact system level architecture?
Well, a little bit, yeah. So we do see a lot of like function as a service type things popping up, particularly in the more web-based workflows. In serverless computing, there's still servers somewhere, right? So it's like saying cloud computing gets rid of the computers. It moves them, but they don't go away. So, but we run a lot of function as a service APIs, and in fact, increasingly, another one of those specialized subsystems is a set aside of nodes for these sort of persistent services that we have to run to make that work well. And yeah, you can use thinner, smaller nodes for that, and occasionally compose other resources. Again, one place I've seen it that I thought it was pretty interesting is building storage servers without the servers, where you just have, trays of drives and a DPU in front of them, a smart NIC with a DPU. And then you do your, you build your aggregated storage systems out of that. And that seems to make a lot of sense to, take the big hefty server out of the storage server, because the DPU can actually do most of the work of just orchestrating the requests to those individual storage devices. So, and for instance, Fungible is doing a lot of that kind of thing. So, and that looks pretty cool too. So, it has to go through sort of the same evaluation process, but yes, we absolutely, see this sort of small transforms and things like that doing. We're not really worrying about scheduling it on a particular server, but nonetheless, I have a pool of servers somewhere to do that stuff. But certainly in our future system plans, we're reserving nodes for these sort of persistent services that have to run like that, because I think they're valuable.
Yeah, they're really user oblivious models, right? Serverless is just user doesn't have to believe there's a server there.
Yeah, you don't pick a node, right? But somewhere I've got to schedule that and run it somewhere. But it's got to match, hopefully in a nice little container, so we don't have to worry about dependencies. But yes, we have thought about, do I need to have as good a nodes to run those, because the pretty short computations, use a farm of cheaper nodes for it, perhaps. Yeah.
We're almost out of time, so I won't get into Taylor's question because it's a little bit more complicated. We'll continue that on Slack, but I just had a quick.
Okay, I'll answer it there.
Just get a quick question into, which was, you just mentioned smart NICs and server nodes, storage nodes. Do you see the same thing potentially happening with smart NICs and GPU nodes, where you don't end up having a host CPU?
Yeah, potentially. I think that's one of the kinds of disaggregation out there, right? I mean, to some extent, when we're putting them in a PCI or CXL chassis, we've already done that, right? We have a tiny little PCI switch controller, and then the software layer of the disaggregation is pulling those GPUs out of the host, so they're a shared resource. But yeah, as a CXL endpoint, maybe tunneled over another fabric, right? But the issue with tunneling them over another fabric versus something like CXL PCI is you're going to add latency, right? So then it's how much does that latency hurt you, right? If we ran, remote GPU over 400 gig E, right, it's going to be a lot higher latency than remote GPU to a CXL box, somewhere. So, maybe these are just rack level fabrics is the way we ought to think about them for disaggregation. But But yeah, absolutely. I think that's kind of what disaggregation is all about in some ways.
Perfect. Well, thanks, Dan, very much for the interesting talk. I enjoyed it quite a bit. I hope everybody else did. Everybody, if you have questions, you can head on over to the Slack channel. You'll see in the Zoom chat, we've posted a link to that Slack channel here if you'd like to go over and continue conversation. But next up, we have Jeremy Launier from Nutanix.
Yeah, thank you, Ryan. Pleasure to be here today. Just some background on myself. I've been working in the technology and the database technology field for the last 2.5 decades or so. Today's talk is really going to be about databases in a hybrid and multi-cloud world, and what sort of trends we're seeing, and where we're seeing customer interest around running workloads across multiple clouds. So I thought maybe we'd start off, we'll just kind of talk a little bit about what are some of the key trends we're seeing in the database market. And really the first trend is that we continue to see more and more applications continuing to rely on databases, whether they be relational or non-relational. In fact, even the recent shift away from monolithic application design towards microservices architecture has continued to result in more and more databases typically deployed and needing to be managed by an organization. This is largely due to the fact that microservices by their nature are really designed to be independent, so that they have no external dependencies, so they can scale and be supported. And that means having persistent data for those microservices. This trend is really resulting in more and more organizations managing more and more databases in their environments. The second key trend we're seeing in the database field is that it used to be the case a decade or two ago that an organization would choose their database platform, and that would result in which types of applications they build on top of that. They may choose to be an Oracle shop, and then they would build their applications around Oracle, or same thing with Microsoft SQL Server. That's no longer the case. It's clearly what we're seeing over the last couple of years is a real shift towards application frameworks defining the database engine. So for example, if you're building applications on top of something like WordPress, you would invariably end up using MySQL as a database engine. And this is largely also due to a shift in influence and control over technology decisions from traditional IT practitioners to development organizations that have more influence over which databases make the most sense for an application. The other key trend we're seeing is a big shift away from proprietary databases to open source databases. So almost all new applications, we've surveyed and spoke to many Global 2000 customers that we support at Nutanix, and the vast majority of them are leveraging open source databases for any new type of application, whether it be Postgres, MySQL, MongoDB, or similar. Yet at the same time, most of these organizations still have a vast majority of their applications leveraging proprietary databases like Oracle Database and SQL Server. And finally, we're continuing to see a continued growth in both leverage and use of both relational and non-relational databases. A couple of years ago, everybody was kind of getting on the NoSQL bandwagon, and there was an idea that, everything should go the NoSQL route. But the reality is that more and more people are recognizing that there's a time and place for different types of databases depending on the use case, whether that be a relational database, a document database, graph database, key value store, basically optimizing for what makes sense for the application. And we continue to see both of these categories continuing to grow. This is just resulting in organizations not only supporting and having to manage, typically hundreds to not thousands to tens of thousands of databases, but also a mix of different database engines, all with their own interfaces, management interfaces, APIs, administrative consoles, and the like. And the last trend that we are seeing in the market around databases is an increased importance on maximizing the productivity of developers and database administration teams. That developers really are looking for the ability to spin up and connect to a persistent data source and tie it to their application stack without anyone getting in their way. And likewise, database administration teams, as more and more workloads shift to the public cloud, are looking to recognize how they can play a more strategic role in influencing the direction, standards, enforcing compliance, and helping organizations to optimize the database workloads that are the most important to those to those organizations. And the end result of all this is we're seeing a rapid increase in demand for database as a service, effectively database automation. Now, what we're hearing from our customers, because Nutanix is in this space, in this database space, what we're hearing, is that there really are four key sort of vendors in the market that offer solutions to solve for many of these database problems. The first, of course, are native database as a service from the hyperscalers, cloud vendors that offer their own database as a service. These solutions tend to be great if you're all in on a specific cloud. They tend to support multiple database engines, both proprietary, like Oracle database, SQL Server, but also open source databases, yet they're limited to a single cloud. And so as organizations mature, as they start to want to look and run and optimize their workloads to run where they're most effective and most cost effective across different clouds, a single cloud solution becomes somewhat limiting. Second category are really database vendors themselves, vendors that have created their own database engine, open source or proprietary, and are offering that as a SaaS offering across multiple clouds. These types of solutions do typically work across multiple public clouds, yet they're limited to a single database engine. And so for most organizations that are driving the choice of database engine based on the application frameworks and based on the developer, the design and architecture defined by development and engineering teams, that becomes very limiting because now you're dealing with different management interfaces, different training requirements, different expertise and skill sets needed to maintain how you consume database as a service across different database engines. And then a third category are multi-cloud database as a service. These are vendors in the market that offer multi-cloud database as a service, typically almost exclusively in the public cloud, nothing necessarily on premises, but they do offer multiple database engines, mostly in the open source space and mostly with containers, Kubernetes-based database services, if you will. And then the final category, the category that Nutanix is also playing in, is really hybrid multi-cloud database as a service. And what that basically means is enabling organizations to take advantage of a consistent management experience, a consistent provisioning and operational experience around their database lifecycle. Very developer focused, easy for DBAs to define standards and to offer that experience in a consistent way across on-premises, public cloud, colos, across multiple database engines. Now, Nutanix customers in particular have been asking for a number of things. One is we typically deal with many customers that are in the global 2000 sort of space, so they tend to have lots and lots of workloads. And usually, that means they may have thousands to tens of thousands of databases across various database engines that they support. And one of the key asks that we hear from them is really they need help to reduce that complexity at that scale. It's really a problem of managing database fleets at scale while maintaining all of their business requirements. So typically, most organizations, they will have a set of business requirements for different tiers of their database workloads and their application workloads. They define security requirements, high availability, how they handle disaster recovery, whether it's disaster recovery to a public cloud or between data centers, how they handle cost and scale and performance. Most organizations are making some sort of transition from proprietary database technologies to open source database technologies. And so they end up having to support both, right? They have different teams that are managing their Postgres environments and different teams that are managing their Oracle environments or their SQL Server environments. And so that adds complexity, right? If they don't have a good way to automate, provide consistency. And organizations are looking to enable their developers, right? To remove any roadblocks, anything that may bother the rest of IT, but in a less PC way, basically getting everybody else out of the way of the developers so they can be empowered to move at their own pace. And then the final problem ask that we are hearing repeatedly from customers, and this is becoming more relevant as more organizations move their application workloads to the public cloud, is they have a strong desire to retain control over their environments. And to talk about control, it's a classic problem of control versus automation. Coming from an on-premises world over the last couple of decades, organizations are used to having a ridiculous amount of control. They have their own data centers, they have their own servers, they have their own storage. They have the ability to customize and tweak the exact builds of an operating system and patch levels and install custom security agents. They had a lot of flexibility to go in and tweak and lock down environments that met all their cybersecurity requirements, that met all of the regulatory requirements. And yeah, by doing so, they mostly had to devise their own levels of automation around how they offer those services and how they maintain those services. And that's very, very problematic in a typical traditional environment, simply due to the fact that they're very heterogeneous, and it's very, very difficult to provide automation around heterogeneous environments. The public cloud, on the other hand, has really provided a high level of automation to the point where a developer could just call an API and request a database, you know, relational or non-relational, and tie it to their Kubernetes environment or to their application stack and be on a merry way. And that's been great for a developer experience, but it's really limited organizations' abilities to go in and tweak and to customize and to lock down or to secure or to meet their compliance requirements, which has been a big blocker in terms of being able to leverage the benefits of database automation, because it means that organizations had to give up control. And we're seeing many examples of organizations that have, as they move workloads to the public cloud, they end up moving their database workloads to IaaS, to infrastructure as a service in the public cloud, instead of managed DBaaS, simply because of the loss of control, right? This is the space that Nutanix is playing in, this space of not only providing flexibility and simplicity for developer organizations, but also making it easy for compliance teams and for database administration teams to be able to define the standards, the builds of software, and to choose and publish those as the DBaaS standard wherever the organization wants to run their workloads. And I think one thing that I think I would like to spend a few minutes talking about is, what do I mean by hybrid and multi-cloud, and why is that important? You know, it's really, it's not a question of, well, people are just going to run their workloads wherever they run it, and so we're just going to end up in a hybrid multi-cloud world. There's a method to the madness. There's a reason why most organizations end up running workloads across multiple clouds and potentially on premises. And it really starts with some key three use cases that I think are probably the most common that you may hear about in the market. The first is disaster recovery. Any organization that has workloads running on premises in a data center or colo may need to provide some sort of disaster recovery. And if they don't already have a secondary site with their own data center that they're managing, that can become quite costly. So one of the most common use cases for a hybrid multi-cloud environment is simply to provide a disaster recovery location in the event that there's a meteor strike or there's some sort of natural disaster in their primary data center. And the cloud can be quite effective for that, because the cloud can be scaled up as needed, right? You can start small. Maybe you don't need to buy all the hardware. You can rent what you need and then scale it on demand as you experience a DR. You just need to get your data replicated, and you can fill up your application stacks at the time of failover. And so that becomes incredibly cost effective. The second scenario that is also quite common is actually variable workloads. This is a natural, right? You know, if you just look at an x-axis of resource consumption, or a y-axis of resource consumption and an x-axis of time, most organizations, if they have a highly variable workload, such as this, a workload where maybe most of the year they may need a small number of systems running an application stack, maybe 3 or 4 systems, and then a couple times a year they see a spike where they may be using hundreds of systems. That's a clear example of a highly variable workload where it really does make a ton of sense to run the public cloud, where you pay for what you need and you consume what you need, and only pay for what you're consuming. There's really no reason to pre-buy or pre-purchase a bunch of hardware in a data center to support that type of use case. There's also, that's a clear example of public cloud. Maybe a good example of the opposite of that is a location-dependent workload. This could be an example of a low latency environment where maybe you're in a factory and your systems need to have super low level latency access to machines on the factory floor, maybe down to the microsecond level. And this is a great example of where you simply just can't get away from running your workloads in your database stacks, in your application stacks close to where your machines are. Another example could be regulatory. There's many parts of the world where workloads have to stay in the same country. They may even have to stay in the same city or in the same data center or in the same vault. So both latency and regulatory requirements for applications are really good examples of why one may choose to run workloads on premises or on a colo that's close to where the consumers of that service are. Yet there are also many other types of use cases that are less obvious, and maybe this is a good example of where we think about, imagine that you are starting up a workload in the public cloud. You start up a workload, you're starting small, maybe you're a new company. Really, it makes very, very little sense to rent or build out a data center and buy hardware for compute and storage. It makes a lot more sense to start in the public cloud and start small and grow. In fact, in that scenario, because you're starting new, the public cloud makes a ton of sense. I mean, you may very well end up paying a very high cost per consumed unit. So the cost per instance per hour for compute or for memory may be quite high, but because your overall consumption is quite low to start with, in the end, it makes a lot of business sense. However, over time, as that workload becomes more steady state, as you get a better sense of how scalable your workload is and how much scale you need, particularly as it becomes more steady state, it may make a lot of sense to look at how you can reduce those costs, right? And to shift to running your workloads in an environment where you have more control over the costs and get to a lower cost per unit. And that's typically where you would see the leverage of a colo. You would also, over time, may get to the point where your workload really ramps up and it gets to a much higher state of usage. And that's another example of where you may want to see further cost savings and drive that into a on-premises sort of environment. And in fact, this is really, this conundrum of the public cloud is pretty well articulated in a paper by Anderson Horowitz. It's a paper called the $1 Trillion Paradox. And in that paper, just to briefly summarize, it basically says you'd be crazy to not start in the cloud and you'd be crazy to stay in the cloud. And it really comes down to the fact that it just makes a lot of sense to start where you have a lot of control over your costs, but over time, those costs are basically profit, by others, the service providers. Now, it's also worth highlighting that this is location dependent. Let's imagine that we started this experience. We launched these sets of applications in the public cloud in Cape Town, and that's fine. And over time, we decided that we were going to go after a market in the East Coast of the US. So we launched a new application and site in New York. We start in the public cloud. Makes total sense. It's a new application. We don't want to build out a new data center. We don't have people that can maintain and manage the data center. It makes total sense to start off in the public cloud. Maybe we start in Amazon Web Services for that. And then we launch a new site in Germany, right, to go after the German audience in the EU. And so we start in the public cloud again in Amazon Web Services. But over time, we come to realize that there are more capabilities at a lower cost in another cloud provider. So we end up needing to to redeploy or to run and deploy workloads in a different cloud. And let's consider a final scenario that we end up acquiring a company that already has workloads servicing their customers on premises. And so these are good examples of where organizations over time will naturally choose to run their workloads where they make the most cost-effective sense, whether it be public cloud, colo, and on-premises. For the last couple of decades, or really for the last decade, there's been a huge shift from on-premises to the public cloud. And that's largely unnatural, in my opinion. The reality is that the reason there's so much shift to the public cloud is because public cloud is new. It's the new thing, and it brings a high level of automation with it, right? Simplicity, agility, the whole bit. But the more natural flow is actually to go from public cloud back to a steady state environment so that you can start small, pay just what you need initially, and then over time get to a lower, much more cost-effective long-term running environment. And so I will close my presentation with that. I want to thank you for your time, and I'm happy. I think we have a couple of minutes, so I'm happy to take any questions.
Thanks, Jeremy. That was a great rundown on hybrid cloud.
Yeah, it's something most people don't think about. They tend to, everybody jumps on the hype cycle of going to the cloud. So I thought it'd be interesting to kind of dissect that a little bit.
Yeah, I certainly know, like, you know, startups think that way, right? They think the opposite way around. They start on the cloud and work backwards. And extracting yourself from the public cloud can sometimes be difficult when you've built applications for a specific vendor. In that space.
Well, and really the key too is that you can't move from public cloud where you have a high level of automation back to on-premises if you don't have the same level of automation. If you're not building your applications on top of, you know, an abstracted, you know, plain or a management environment like a Kubernetes cluster, or building redeploying your applications from Terraform or other, you know, automation tools, it becomes a lot more difficult, you know, to get the cost benefits of running on premises. So you really have to have that level of automation wherever you want to run your applications. But in the end, it really does give organizations a lot more flexibility to run their applications where they make the most sense.
Yeah, there's certainly a skills gap there that you need at your org before you can bring things on-prem that it is not there when you first start out in cloud. So.
Great. Okay. Well, thank you.
Thank you. There is a Slack channel set up so that you can chat during the break with Jeremy. So anybody has any questions or would like to discuss things more, I'm certain there's some interesting hybrid cloud discussions that can happen over there. Please check out the Slack channel for doing that. It's Diamond sponsor Nutanix. And we are now going to go on a break, and we will be back at 35 minutes past the hour. So roughly 13 minutes, depending on your time zone. So at 10:35 Pacific time. Everybody remember that we're going to switch channels in the Zoom client. So go back out to your lobby and we'll start session 2. Thank you very much and enjoy the break.
Thanks, Ryan.